Okay, folks, this video is going to be my first sort of intro video for section 2.5 on the idea of continuity, okay? What this question actually is, this is actually a homework question from section 2.3. This was question number 12. The student who emailed me in particular had these red digits, a 6 and a 3, so I just drew them red right there. Just to kind of mention, if you guys see red digits in your WebAssign, that means other students may have different numbers. A few students probably have the same numbers as you, so some of you guys might have a 6 and a 3 here. Other folks might have other numbers, but the concept is the same, okay? So I just wanted to make that point, but let me fill them in black so they don't look special. All right. And so this problem on the homework back in 2.3 has 6 different parts. They're asking for a couple limits from one-sided limits, a couple function values, and things of that nature. What they're really exploring is whether or not this function is continuous at certain values. Okay, so I want to talk about that. So I'm going to kind of go over this question from the homework, but sort of rephrase it in the context of continuity. Okay, up here is just essentially it's our definition of continuity, but rephrased sort of in question form, because I'm going to answer those questions for some x values over here. Okay, we defined, in the definition we used a function called f. Here I'm calling my function g, so all my function notation just says g, but the same thing. And I want to know about is this function g continuous at certain x values? We use a sort of as an arbitrary quantity right there. And so we had, if a function g is to be continuous at this value when x is a, then remember there needed to be 3 things that are true for the function to be continuous. The function has to exist there, meaning so g of a has to exist. That has to actually be a function value. The limit has to exist. So as we approach that value, there has to be a well-defined limit. And then finally, the limit should be the same as the function value. So sort of the function value should kind of like fill in the gap that the limit might leave. So that's the idea right there, okay? So the homework question had some specific limits, but let's look at this. Let's say it wasn't the homework question and you were just given this function and you were asked to sort of discuss the continuity. All right, discuss the continuity. Sometimes some upper division math, they kind of use that phrase, or even in this book, they might just say discuss something. What does that mean? Well, that means if we were together, we kind of analyze it together, I guess you could say. So if I was up on the blackboard at school and you guys were sitting there, I'd probably be asking a lot of questions and kind of more of a back and forth. But I'll just kind of reason that out together. So first of all, let's look at the pieces. This is a piecewise function. I've got 1, 2, 3, 4 different rules, all right? All of these rules individually are polynomials. Meaning if I have just the line y equals x, right? That's just a polynomial. That's just a straight line, slope of 1. I think you would agree that is a continuous function on its own right. It's just a straight line, has no gaps, nothing crazy going on. The next piece, 6, that's actually only existing at one point. But if you've got the curve y equals 6, again, that's a straight line as well with slope 0. That's just a horizontal line whose y-coordinate is 6, a continuous piece, right? So these pieces are continuous themselves. 2 minus x squared, that would be, the x squared tells me I've got a parabola. The minus sign means it's been flipped. I've got 2, so that's kind of a downward-facing parabola. Looks something like that, right? Of course, now, for this piecewise function, the function g is only defined using this rule for certain x values, right? So I'm not claiming that the graph of g is going to be this parabola. But this piece of the function is a parabola, which is a type of polynomial, and that is continuous in and of itself, right? And then finally, the line y equals x minus 3 is another straight line, right? You could graph that. That's a straight line. That's continuous. So we're going to kind of take for granted that polynomials are continuous. Their domains are all real numbers, and they're nice and just smooth functions, well-defined everywhere. They don't have holes. They don't have gaps. They don't have asymptotes, right? So these pieces are by themselves continuous. But because I've got a piecewise function, the rules change, right? So if I've got a continuous piece, if I've got a function that looks like this to a certain point, I can say that thing is continuous, right? And then if I've got another piece over here that looks like that maybe, I can claim that this thing is continuous, right? So this piece is continuous, this piece is continuous. That's what I mean about each 4 of these pieces being continuous. However, if I've got some x value a right there, and now I told you that these 2 pieces are really part of the same piecewise function. If I said, is this function f continuous at the x value a, you'd say no, right? And let's see what's being violated. Does f of a exist? Yes, that's at that dark dot, right? So that height would be f of a right there. Does the limit exist for this kind of function f that I drew? No, right? Criteria 2 is being violated. Why does not this limit exist? Because as I approach from the left, I'm going up here. As I approach from the right, I'm going down here, right? So the left-hand limit is this height. The right-hand limit is that height. So the overall limit doesn't exist. We violated criteria 2, not continuous at a, right? But that's pretty straightforward because we can see the break. However, when we look back to a piecewise function, if we don't have the graph, how do we really know where things are linking up, okay? So, again, this comes from section 2.3, question 12, which asks you for specific limits. But let's think about, let's reason out. We can figure out what the questions would be, right? WebAssign's not going to ask useless questions. Sometimes they do. Sometimes they ask tedious stuff. But in this case, WebAssign is not going to ask useless stuff. They're going to have us investigate continuity, essentially, at x values where the continuity might be discontinuous, where the function's changing. In other words, each piece is continuous, but here, the function is defined at, when x is exactly 1, it's just defined at this height 6. But then for values less than 1, we're using a different rule, and for values greater than 1, I'm just looking at that piece of the inequality right there, for values greater than 1, we're using this rule, right, within a certain distance. And so on either side of the value when x is 1, who knows what the function is doing, right? Who knows where they're going, if the limits are going to exist from those sides, and if they're going to match the function value. So 1 seems like a spot to investigate. And then the other spot to investigate would be when x is 2. Right here, when x is less than or equal to 2, the function is defined by one rule. But then when x is greater than 2, it's defined by a different rule. Right? So imagine that graph I just erased, right? It's defined one way here. This piece will be continuous. It's defined another way for x greater than 2. That piece will be continuous, but are they going to link up, right? If they link up, it's continuous, or are they going to have some kind of gap between them? So we want to investigate each x value separately. First, we want to look at 1, and then we want to look at what's going on when x is 2. All right. So I put up these 3 questions, right? I'm going to ask myself, is this function continuous when x equals 1? Okay, so that's the first question we're going to ask ourselves. So just change those a values to 1. And there we go. All right, green pen. Hopefully that's visible. So let's jump in here. So the way I'm going to do this, because of the way I phrase these questions, is slightly out of order from the homework. The homework has you look at the left-hand limit and then the right-hand limit for 1. Let me answer this question first, though. Does g of 1 exist? So first of all, yes, if I'm answering the question, yes, it exists. G of 1 is equal to, so g function, if the input is 1, and on the homework or in WebAssign, all of these have if statements. So if you prefer the if statement, if x is 1, then g of x is going to be this 6, right? That's the way we read those things. So g of 1 is 6. Okay, so does g of 1 exist? Yes, it's equal to 6. Cool, so we got the first, at least the function is defined there. If it wasn't, then we definitely don't have continuity. So g of 1 is 6. Let me put that up top. All right, so we answered the first question. So we're on the right track. Question 2. Does the limit as x approaches 1 of this function g of x exist? Okay, how do we show that for a piecewise function? And so that's, I think, what was probably tripping up the student who asked me about this. So what I need to do is, because as x approaches 1 from the left, the limit as x approaches 1 from the left, remember when I first introduced this notation, I said you could determine that as 1 minus a little bit. Right? If we're approaching 1 from the left, then we're approaching for values less than 1. Right? Meaning values less than 1. So the limit as x approaches 1 from the left of our function g is going to rely on this rule, right? Because if x is less than 1, then that includes all these values to the immediate left of 1. So we're going to rely on that rule. So we'll come back to that. And let me just set up the limit as x approaches 1 from the right of my function. As x approaches 1 from the right, if I go really, really far to the right, you know, by like 5 or something, then that 5 is greater than 2, right? Then the function would be following this rule. But if I'm approaching 1, then you can reason out that we're getting pretty close to 1, right? So I want the inequality involving a 1. So I'm looking at that piece of this inequality right now. So if 1 less than x, you can retranslate that as x greater than 1, right? So if x is greater than 1 and still under 2, then we're going to follow this rule. All right, so we're going to have to plug in 2 different rules here. The reason why we are using, why we have to immediately invest, well, again, the homework asks you for these two, but if we're in chapter 2.5, section 2.5, and I just ask you, does this limit exist? For a piecewise function, you always have to do this. Consider the left and the right-hand limits, because we've got 2 different rules, right? So there's nothing built into the function that means they're going to have to link up, right? It's really just up to what these rules say. So the way I like to set these up to make it clear what I'm doing is first say this: the limit as x approaches 1 from the left of my function g, just to make it clear that we're working with the function g, right? But from there, I'm going to say that's equal to the limit as x approaches 1 from the left, and I'm going to replace g with the specific rule that holds up for x values to the left of 1, meaning these x values, right? So when x is approaching 1 from the left, this is the rule we're using. And so I'm going to replace my g with just the function right there, just what the rule of the function says. All right. And from there, since these things are all kind of polynomials, all nice, well-behaved functions, from there we do direct substitution. All right. And I'll have to explain that exactly what's going on, though. But we're going to let x go to 1, right? When we're doing direct substitution now, we don't care that it's going from the left or from the right. We're actually going to plug 1 in. So I'm going to do direct substitution right here, which means I'm going to stop writing the limit notation. I'm going to let x actually go to 1, and so then x went to 1, right? That's what we just said. Okay. Before we talk about the right-hand limit, though, let's just back up, because in the past, and even now, I can see why students might be confused. You say, wait a minute, though, if x is 1, why am I plugging 1 into this rule, right? If this rule is only defined for x is less than 1. Right? If x is equal to 1, I thought we're supposed to use this rule, right? So why am I plugging it into the first one? Well, it's because we're taking the limit, right? So when we did the function value, g of 1, where the function actually lives at that very one spot, there's only one little point here, right? This is only defined for one single point. At that point, the function lives up at 6. But as we approach that point from the left, but just in general, as we approach it, we're following a different curve. Right? And so this limit equals 1, the graph we'll see is going to have a hole at 1, or we'll depict it with a little open dot to indicate that the function is going there, but then it's living up here at 6, right? It's living up there at 6. And so that's why we're plugging into that one. So let me do the same thing for the right-hand side, and hopefully this will make sense. So the limit as x approaches 1 from the right, or from 1 plus a little bit, again, that means these values right here, when x is larger than 1. So the limit as x approaches 1 from the right of our function g is really means the same thing as the limit as x approaches 1 from the right of the rule for those particular x values to the right of 1, directly to the right of 1. And so that's going to be evaluated by 2 minus x squared. Alrighty, and then we'll do direct substitution there. At this point, in the context of continuity, we can already tell that this function is not going to be continuous at the point 1, right? Although we don't know which criteria got violated yet. That's why we want to finish this thing. But how can we tell that? Well, there's 2 scenarios that can happen right now. If this equals 1, if this also equals 1, then the limits are the left and right hand limits are the same, which means the limit exists, right? But if that's going to be the case, then the limit's going to be 1, which is not the same as 6, right? So if this limit exists and is 1, then it's not going to be the same as 6, so we're going to violate criteria 3. Another option, though, that could happen right now is, who knows what this becomes. If this becomes something other than 1, then that means the limit doesn't even exist, right? That means the left and right hand side were different, and then we're violating criteria 2. So let's roll with it, though. So again, we're doing direct substitution, not because g of 1 tells us to use that rule, right? G of 1 is using this rule, but as we approach 1 from the right, we're approaching for values slightly larger than 1. And so for those values, we have to use this function, and then we can see where they're trending, where the open hold will be, the little dot, by plugging in the 1 into that. And so we're going to get 2 minus 1 squared. Notice I didn't write limit, right, because we took the limit. We let x go to 1. We're plugging it in. So that's direct substitution right there. And 1 squared is 1. 2 minus 1 is 1. Okay? There we go. So in the homework, I think this is part A, question A. This is question B. And then they had up here was question C, right? And again, they're not addressing continuity per se because we're back in section 2.3 where we didn't have the idea yet. But let's see what's going on. Does the limit as x approaches 1 of g of x exist? The answer is yes. The answer is yes, it exists, and the limit is 1. So I could write that in my own notation now. Limit as x approaches 1 with no superscript of my function g is equal to 1. All right, that's true because the left and the right-hand sides agree. So even though we had two different rules, they kind of match up. So kind of cool. So the limit exists, but by the time you get to step 3, there's really no work to show. You just look at what you've already done. The function value is 6. The limit is 1. So instead of putting an x that looks like an algebraic term, I'll put a little sad face. Does this limit equal the function? No. So the function's, does the limit equal the function value? No, and so the limit is, the function is discontinuous at that point when x is 1. Okay? When we're all done with this, I'm going to show you quickly kind of how to graph a piecewise function, kind of go through that, and well, I'll commit this to memory, or I'll write it up here. Limit as x approaches 1 is equal to 1. So that can be helpful. Okay, so we know that. Cool, so let's do the next one. So the next 3 problems on the homework asks you for, now we're all concerned with 2. So it asks for the left-hand limit as we approach 2 from the left. It asks for the limit as we approach 2 from the right. And then it just asks for the overall limit. It doesn't ask for the function value, so I'll probably go a little bit extra. But let's dive in. So let's change this question. Is this continuous when x equals 2? All right, so change all the 1s to 2s. G of A, we're letting A be 2, essentially. We say x is 2, A is 2. X is sort of the variable, A is then the particular x value, so there we go. Let me erase these things. Okay. First of all, the homework doesn't ask it. Homework 2.3 doesn't ask it, but let's do criteria 1. Does G of 2 exist? Yes. G of 2 is what? Well, this said I use this rule if x is less than or equal to 2. So I'm going to use this rule for the actual function value. And then I'm also going to use this rule for the left-hand limit as we approach 2 from the left for x values that are less than 2. So this symbol, the less than or the equal to, kind of using each piece in a different spot of this examination up here. So G of 2, if x equals 2, just plug it into that. So I'm going to get 2 minus 2 squared. So 2 minus 2 squared equals 2 minus 4 equals negative 2. Okay, so that exists. So G of 2 equals negative 2. Alrighty. So criteria 1 satisfied. Good enough. Criteria 2. Does the limit as x approaches 2 exist? And so again, this is what's being tackled now in the homework when they ask you limit as x approaches 2 from the left, and then limit as x approaches 2 from the right. All right. And so both of these functions are called g. It's the same function. So this function is called g, I should say. But then now I'm going to substitute each piece with which piece of the function I would use based on those x values. So as I approach 2 from the left, we're approaching for x values at less than 2. And so I want to use the 2 minus x squared. So limit as x approaches 2 from the left of 2 minus x squared. Okay, and we can do direct substitution for that one. And as I approach 2 from the right, that means x values that are larger than 2, so I'm going to use this rule. So I'm going to have the limit as x approaches 2 from the right of x minus 3. Okay. So notice, remember when I calculated g of 2, I plugged negative 2 into this rule. because of the equal bar right there. Now I'm plugging 2 into the same rule because of the less than, right? But the calculation is exactly the same. I'm going to get 2 minus 4, and we're going to get negative 2. Okay? We're not done yet. We don't even know if the limit exists yet because we have to look at the other side. But things are looking kind of good in a way. I mean, the function value matches at least one side of the limit. But that should be obvious by that, right? The less than or equal to means the limit is the less than, the equal to is the actual point. Same rule, should work out. What's going to happen over here? As x approaches 2 from the right, we're using this rule, so plug 2 in, and I'm going to get 2 minus 3, which is negative 1. All right. Both of those steps were direct substitution. When I plug that actual 2 right there, right, we plug the 2 in here, plug that 2 right in. Actually, that was 2 squared, but whatever, we got it. Anyway, left-hand limit does not equal right-hand limit. Sometimes I just sum that up with my own little notation. Left-hand limit does not equal the right-hand limit. All right, so just to kind of save time, does this limit exist? No. Let's put our sad face. Does not exist because the left-hand right and the right-hand limits don't match up. All right, and then therefore we don't even have to ask this question, right? That was the metaphor I made in class about does your grandfather, is he the same as Santa Claus, right? Well, if we agree Santa Claus doesn't exist, then the question of his secret identity doesn't even really make sense. So that's the concept right there. Let me just jot these limits down. Limit as x approaches 2 from the left of g was negative 2. Limit as x approaches 2 from the right of g was negative 1. Just to keep track of that information, because that's going to help me graph some things right now. All right. Okay, so up here I've got all the information. I have the original function. Let me erase. So we finished all the homework problems right there. The very last part, obviously I said this guy limit does not exist. Let me erase all this stuff and just show what the graph looks like. So what did we show? We actually showed to conclude that this function was discontinuous when x is 1, right? And the reason is because criteria 3 was not satisfied. The limit existed, but it wasn't the same as the function value. And then what we just saw is when x is 2, the limit didn't even exist. The left and right hand sides were going to 2 different spots, which means there's some kind of jump in the graph, and so it's also not continuous there. And along each one of those parts, though, you could argue it's continuous. Again, this is just going to be a single point, but the rest of them are going to be continuous pieces. So let's look at that. There's all our information. So I'm pretty good at graphing things, kind of rough sketch I call it, or sort of a rough graph. In other words, I'm not going to make a table and plot a bunch of points here. I could do that. That's time consuming. When I teach pre-calculus, there's a section called parent graphs, and I think we had a section in one of the early homeworks called like essential functions or something like that. Parent graphs help us just sort of imagine the basic shape of a graph, and then I can use like 1 or 2 points to kind of get the idea. But I'm not going to go crazy graphing this super accurately. But again, I mentioned earlier, this thing is the line y equals x, right? That's a point when x equals 6. This is a downward-facing parabola, and then this is another line, right, with a slope of 1. The intercept would be here if the function was defined that way when x is 0, but it's not. But we can kind of use that as well. So if I'm going to set this up, the x values I'm concerned with are 1 and 2. So I definitely want to make sure 1 and 2 are on my x-axis, because that's where we were all kind of concerned with. And I want to spread out a little to either side so we can see what's going on. And my y values that I ended up with are either our function values or our limits. So I see the height of 6 is up here. I see some negative values, negative 2. So I'm kind of just taking all that in to think about how I want to set up these axes here. So let's say I've got something like that. And so I'm concerned with the x values of 1 and 2, and I want to go a little bit beyond. So let's say 1, 2, 3, and 4. All right, so each one of these marks is just a unit of 1. If you can see those, let me darken those up. All right, I'll put a 4 out there. Let me come back to like a negative 1 just so we can imagine what's going on over there. And let me stack up. So I want to go to a 6. So let's say 1, is that going to work? 1, 2, 3, 4, 5 and 6. All right, way up there. And I want to go down to a -2, -1, -2, maybe a little extra, -3. Alrighty. So there, we got a couple of coordinates there. Let me try to graph these pieces now. So how do I want to start? You could just start at the top and go down. Let me try to be a little strategic here. This is just a single point, right? If x equals 1, that's just one isolated point. When x equals 1, the function value is 6. So that's this guy up here. G of 1 is 6. So that point lives up there. All right. I'm going to plot limits now. If they don't live, if I had an open dot right there, right? If the limit approached there, and then the open dot would, the circle would fill in the open dot, and they would link up, right? That will happen with a lot of these piecewise functions that you do for homework. But that didn't happen for here. But let's use this. The limit as x approached 1 of the function g was the height of 1, right? That means as I approached 1 from the left or from the right, the graph was going to this height of 1. So that means I can put a little open circle right there. Right, and so that's not really a point on the graph, it's sort of a void, but from the left and the right, whatever I draw, the pieces of this graph are going to approach that open circle. And so that's helpful, so I want to use that for my advantage. So let me plot some other stuff here. So g of 2 is -2, okay? So if I come over to 2 here, then I'm down to the height of -2. So g of 2, that's a function value, so g of 2 is -2, means I've got a closed dot right there. Right, that function value actually exists. As I approach 2 from the left, the function was also going to that -2, right? Which means I don't know where it's coming from yet, but it's going to hit there from the left, right? So I'm not going to draw anything yet. I'll wait till I start graphing the actual piece of the function in here yet. But the graph looks something like that. The limit as x approaches 2 from the right was -1. Again, that's not that's like this limit. It's not, doesn't match up with the function value, but it's still useful information. That means the function is, as I trend towards 2 from the right, the function is trending towards the height of -1. So again, let me put an open circle at that spot. I know a function from the right is going to sort of terminate at that little circle. Okay. There. So we got we got the limits and the points that we plotted. So not a ton of stuff, but let's see what else we can get out of this. I'm going to erase those items now because we've got them all graphed, just to give myself a little more space here. Let me graph this thing now. The line x, if x is less than 1. Okay, what is that? That's the line, the curve y equals x, which if I sort of embellish that as the equation of a line, the slope there is 1, right? 1 times x, and plus 0 is the y-intercept. Right, so that's a slope. That would be a line that it's defined for all x values less than 1. So everything to the left of that mark. So everything back here. So it's passing through the origin. That's its y-intercept. Its slope is 1. Let me graph that piece in some purple. Okay, so that's passing through the point 0, 0, passing through the point -1, -1, and so forth. So it's just coming up like this. The limit as we approach from the left was 1. So it's going to there, right? It's going to that open dot right there. We don't fill in the dot, but it stops right shy of that dot, right? So that little piece, and you can put the little downward facing arrow down here to indicate that we keep continuing. Okay, so we graph that thing right there. This thing, the 6, again, that's just one single point. If that was defined over an interval, it would be a horizontal line. That would just be the line y equals 6. But here, that's just defined at one particular point. So let's leave that alone. Let me skip the parabola for a second, because it's a little bit trickier. Let me do the line x minus 3. Okay, let me do that in some blue ink. So I'm looking at the line y equals x minus 3. The slope of that line, again, is a 1. So that's probably the most helpful part, because the y-intercept, what I've had students do in the past when they're trying to graph these things, is they graph the line x minus 3. So they say, oh, that has a y-intercept of 3. And then they sketch this line that looks like that. And the problem is then you've got the purple line and the blue line, and if you draw a vertical line, you're crossing the graph at 2 spots, which means it's not a function. So then you're violating the vertical line test. So we're not supposed to do that. This graph only sort of takes over this rule to the right of 2. So sometimes it's helpful to draw that. So let me clean that up a little bit. I'll draw a dotted line, and then, So one thing I recommend for students when they're doing this on paper, if you like, is you can draw all the functions completely using a pencil and then erase the portions that don't belong. If I was just graphing this line, x minus 3, the y-intercept would be 3, right? The x-intercept is also going to be 3. The slope is 1, so I'm going to go up 1 over 1 to there. Up 1 over 1. I would go through that little hole. Up 1 over 1 there. And so I would have this line right there with slope 1. Right? Remember, the purple line had slope 1 too. So those guys are parallel. They have the same slope. So what I just graphed, that dotted line, is just the complete line y equals x minus 3. However, the rule for that line only takes over for x greater than 2. Okay? So you can use that line if you want, if the intercept is helpful, and then just erase the portion that's less than 2. Right? The function's not defined that way for x less than 2, so we erase that portion. It's not defined that way for x equals 2. For equals 2, it's up there. So that's why we've got the open dot there. But for then x greater than 2, then this line picks up. The function starts behaving like this blue line. All right. There you go. And if you don't like the whole business of erasing, just use the slope. If you realize that it's a line, the slope is 1. Remember, the limit is kind of like a point on it, except it doesn't really exist, but we've got that thing. And then so from there, if I go up 1 over 1 for the slope, I hit that. Up 1 over 1, I'm back on the curve. So it works out like that as well. Okay? So the only thing I didn't graph yet is this thing, 2 minus x squared in this little interval between 1 and 2. That's the last piece I have, right? And so I mentioned earlier, 2 minus x squared is a downward-facing parabola, right? But we've only got a piece of that. So it's not like if I did this in red real quick, it's not necessarily that I'm just going to connect those things with a parabola, right? I kind of want to see where the parabola might go. So this one, if you were trying to plot this real accurately, you could find some function values in between here. So you could do like f or g of 3 halves, right, would be that midpoint right there. G of 5 fourths, G of 7 fourths, right? You could break this interval up, plug in some function values, plot them, and get the heights like that. We know this point, I'll do this one in red, 2 minus x squared. We know 2 minus x squared is going to be on, it's going to hit that point, because that was defined when x was equal to 2. We were using that rule, okay? Let's think about what the graph is. This is a graph, 2 minus x squared. If I graphed it everywhere, it's a downward-facing parabola. If I plugged 0 into that, I would get 2, right? 2 minus 0. So if the parabola existed everywhere, its vertex would be right here. All right? Its vertex would be right there. When x was 1, remember, the limit, when we calculated, I erased it now, but when we wrote this, the limit as x approaches 1 from the right, our overall limit was 1. That's why I drew that open circle right there. As we approach from the right, the height was 1, right? And as we approach x from the right, that inequality, we were using this rule. And so you can imagine that the downward-facing parabola would pass through that point on both sides. It would be symmetric, and then it would keep coming down and pass through that dark point, that black point, and then keep going, right? So I did that in dotted form, so it's not too visible on camera. But if you look at this, follow the tip of my pen right there, that's a downward-facing parabola. Right, symmetric about the y-axis, got this vertex. We know a couple of points that it passed through. So that's that graph right there. That's how it would exist everywhere. But now that only exists for x is strictly greater than 1. So right after this, where this hole is, it picks up. And down to and including, I don't want to go over the black, but including that function value down there. Alrighty, and let me now erase the rest of that stuff because I don't want to violate my vertical line test. Okay, and so by doing that, again, this is kind of freehand, not perfect, but what I was aiming for is to sort of have a little of this parabolic curve on that thing, right? This is not really a straight line. It's sort of a little chunk of a parabola, so it should look a little curvy right there. That thing was supposed to look like a straight line. I freehanded that, so that actually looks curvy. But that was just the straight line with slope 1. The blue is just the straight line with slope 1. This function is defined everywhere because it's defined for x values less than 1. When x equals 1, it jumped up there. Then as we go x greater than 1, but still less than or equal to 2, we're following this curve down there. And then as soon as we get greater than 2, it just picks up for the rest of it. All right. So, kind of a long Very long video right here. But basically, that's a great example for section 2.5 already. So that shows how to evaluate these piecewise functions. Perhaps something like this might be one of our paper assignments. Maybe that first paper assignment. Maybe I'll assign on Wednesday. Maybe do over the weekend. So give you guys a couple of days to think about it, write it up neat. But anyway, hopefully this was useful. If this enlightened you and you want to reopen question homework 2.3 so you can tackle this homework question again, by all means send me an extension request and we'll go from there. All right, folks.